Okay guys, now on chapter 14, heat problems, exercise 14F, this is where we calculate the total amount of heat we need to go to add in order to get from really cold ice to really hot steam or anywhere in between. And that heat capacity, the heat curve is really important to think of. You may not think that ice can be really cold, but it can. And so if we start adding heat to some really cold ice, remember that heats up the ice. Then there's a change of state of matter whenever you add heat. Whenever we melt the ice, then you can heat up the water. Then another change of state whenever we churn water into steam, and then we can heat up the steam. Remember, for change of state of matter, we don't change the temperature, we merely add heat to change the state. So heat of fusion times the mass is for the heat of fusion, and the heat involved with either condensing, if we're going that way, cooling things off, or vaporizing. Heat is equal to heat of vaporization times the mass. But for all the other possibles, A, C, E, along the chart here, we are just using the same state of matter. We're heating up ice, we're heating up liquid water, or we're heating up steam. Since we have the same state of matter, we can use the same heat capacity, and all we're doing is looking at the change in temperature. Okay, so we simply follow along on this problem and take care of each of these different stages and calculate them. Alright, so let's get started. A, we start with ice at minus 17 degrees C. What happens whenever we add heat to ice at minus 17? We do not melt it, because ice doesn't melt until it gets to 0. So how do you get from ice at minus 17 to 0? Change of state of matter? No. So instead we're just going to do mc delta T. The mass is 12.5 grams. The heat capacity, well, which heat capacity do we use here? Ice. To use the heat capacity for ice, that's H2O solid, really important. Calories. H2O solid is 0.498 calories per gram per degree C. Make sure you use the right heat capacity for the different states of matter. So 0.498 calories per gram per degree C. And what's the change in temperature? We're just doing this first little section here. So that's negative 17 up to 0, or 17 degrees C. Okay, so we have to figure out what that is, and we have to keep track of the sig figs. So what is 12.5 times 0.498 times 17? I get 106 calories. And how many sig figs is that? That's 3, that's 3, and that is 2. So we're just going to draw a 2 here, keeping track. Alright, so that's the first stage. We've heated up the ice. What happens whenever we take ice at 0 and we add heat to it? It turns into liquid water at 0. Now you can't use H is equal to mc delta T here, can you? Which heat capacity would you use, for ice or for liquid? What temperature change would you have? 0? Does it really not take any heat to melt ice? Of course it does. So instead, this time you have to use mass times the heat of fusion. So that's 12.5 grams. And what's the heat of fusion of water in calories? 79.71 calories per gram. 79.71 calories per gram. Grams cancel. We're going to add up this many calories. 12.5 times 79.71 is 996 calories. How many sig figs? 3, 4. So this one has 3. Let's keep going. We've done this. Now we're going to take liquid water at 0 and add heat to it. Well, it gets all the way to 100, right? H is equal to mc delta T. Why can we use mc delta T? Because there's one state of matter, liquid, and there is a change in temperature. Maybe the problem wouldn't have asked all the way to steam. Maybe it would have said liquid water at 73. So you'd finish at 73, find out what that delta T, add those up, and you'd be done. But for this problem, the mass is 12.5 grams. The heat capacity for liquid water, right? Now we're going to do liquid water, and that's 1. 0.000 calories per gram per degree C. And what's the temperature change? It's this, not that. So it's just 100 degrees C. So what's this add up to? Let me see if I can move this up here. I'll move this real fast, because I want to make sure everything lines up. .5 times 100 is 1250, right? 1250 calories. How many sig figs is that? That's 3, that's 4, that's 3. So that guy's going to have 3. So we've heated up the ice. We've melted the ice. We've heated up the water all the way to 100. What happens when we add more heat to water that's at 100? We start to boil it. We convert it into steam. Change of state of matter. No change in temperature. Can't use this. Have to use the heat of vaporization times the mass. 12.5 grams. What is the heat of vaporization? In calories per gram, 539.5. Cals per gram equals, and again to 3 sig figs here. Let's see, 4, 7, 6. Okay. 3 sig figs. Alright. One final move. Heated up the ice. Melted the ice. Heated up the water. Converted it into steam. Now we're going to heat up the steam. So the final part to the heat curve. Steam at 100. To steam at the final temperature that they want, they say 632. Okay. Same state of matter, changing temperature, mc delta T. Right? The mass is 12.5 grams. The heat capacity this time, H2O gas, 0.480 calories per gram per degree C. It's a common mistake. Be careful. Make sure you use the right heat capacities. And what's the change in temperature here? To get from 100 to 632, it's 532, right? It's important that you get the right change. So what's 12.5 times 0.48 times 532? 12.5 times 0.48 times 532. 3192 calories. Adding all these up, right? But first, 3 sig figs there. Okay. So, how do we determine the sig figs whenever we're doing these addition and subtractions? Well, let's do the raw calculation first by adding them all up. 3192 plus 6744 plus 1250 plus 996 plus 106 equals 88221 calories. That's the raw number. How do we figure out significant figures? Well, this is an addition subtraction. So you don't just pick the smaller number, right? Instead, you have to draw the line to the least number of places passed. It is important that you understand here that you can convert all these to exponentials, but I don't recommend it. I think this is the easier way to do it. Think about where you're drawing the line here. If you were going to write this number to 2 sig figs, wouldn't you write this as 1.1 times 10 to the 2? So it's known to the tens place, right? Or in other words, this is where you would draw the line, right? To the tens place. Where would you draw the line here? To the ones place. Okay? But if we're adding a number to the ones place and a number to the tens place, the best we can do is the tens place. So we're still drawing the line here. Now what? 3 sig figs. This is the best we can do, right? This is to the tens place again. So we're still drawing the line here. 3 sig figs. This is known to the tens place as well. So we're still drawing the line to the tens place. 3 sig figs once again. So we're drawing the line to the tens place. That's where we draw the line. Just because we draw the line to the left of the decimal doesn't matter. It's the least carefully measured number, and that's to the tens place here in the answer, right? So, if this is the decimal, it has nothing to do with the decimal. There's no reason why we can't draw the line to the left of the decimal. So the tens place is the answer. Has to be to the tens place, which means 4 sig figs, which means 1, 2, 3, 4. And we're writing the answer 1.229 times 10 to the 4th calories. Here, even though that had 2 sig figs, 3 and 3, the answer had 4 because of how we did our calculation. That's a sig fig issue that you have to be careful with. Practice at it, you'll be good. Make sure you draw the line to the least number of places past the decimal point. In this case, the best we can do is to the tens place. Okay, good luck.